Hey everyone, so today we will be talking about solutions of non-homogeneous linear ODE and superposition principles. So to do superposition principles as well as solutions towards the non-homogeneous linear ODEs, you will need to remember this general solution, which is y equals to yc plus yp. So note what is YC. YC is the general solution of the corresponding homogeneous ODE, or called as the complementary solution or function, whereas YP, on the other hand, is a particular solution to the non-homogeneous linear ODE. So without further ado, let's go to our first example. Hey everyone, so this is our first example for today's solving solutions towards non-homogeneous linear ODEs as well as superposition principles. So to start off, with this problem, we need to start with the superposition principle itself, which is y equals to yc plus yp. And to recap, yc is a complementary solution or the general solution of the corresponding homogeneous ODE. However, the yp is a particular solution to the non-homogeneous linear ODE. So to start off, let's start by solving the yc or the complementary solution to this ODE. So yc is just the second derivative of y plus 9y equals to 0. And let's do our same exact steps, which is converting this ODE into a characteristic polynomial and solving it to see how many roots we get. So r equals to square root of 3, and this makes it into actually -9, square root of -9, and square root of -9 will just be 3i. And we all know this is a complex case, so we're going to use the third case for this, which the third case equation is equivalent to yc equals to e to the alpha x multiplied by cosine beta x plus sine beta x. So we're not going to use our given solution here, but I just want to show you all that through doing the same exact steps like what we always do in the previous lectures of this ODE series, we can get the same solutions as what provided here. So after you know how to do the steps to get this both solutions up here, you can just skip all of these steps and just straight up write down the solutions which are up here, y2 and y1x. So, but before doing that, let's continue solving this. So we know that alpha is 0 and our x is 3. So this is just going to, yc is just going to be e to the 0, x is just 1, e to the 0 is 1. So cosine, actually we may be forgetting our c1 and c2 here. So this c1 times cosine beta x plus c2 times sine beta x. And I'm plugging in our x's, which is 3. So c1 times cosine of 3x plus c2 times sine of 3x. And so this is our general solution for our yc. And notice here that we got the same exact solutions as it was provided at the start of the question. So basically, the general solution of the complementary solution is just c1 times y1 of x plus c2 times y2 of x. So if you know how to do all of these steps to solve an ODE and choose either one of the three cases and get the general solution for the complementary solution, and if you're given the solutions at the start of a problem, you can skip all of these steps and just jump right in by plugging in the y1x and y2x and leave the complementary solution as your answer, as it is. And so we got and we've proven our general solution for the complementary solution, which is correct. And now let's try and find our particular solution. However, notice that we've given a particular solution up here, and so we don't need to try and find the particular solution again for yp. So yp is just equals to 3, and we've got our yc and yp, and let's just plug both of them into our superposition principle, which is y equals to c1 cosine of 3x plus c2 sine of 3x plus yp, which is just 3. And so this is our general solution for this question. However, notice that we've given us initial value conditions to deal with. And how to do that, like in our previous lectures, we just need to plug in the values, and if there's a derivative of y derivative 0 equals to 2, we just need to take the derivative of our general solution and plug in the values, and so we get the solutions to our unknowns. So let's start with y0 equals to 6, because we don't need to do anything with the equation, with the original equation. So this is practically easier. C1 times cosine 3 times 0 is 0, so cosine 0 is 1. So C1 plus C2 sine of 3 times 0, sine of 0 is 0, so C2 times 0 is another 0. So this C1 plus 3 equals to 6. And we get our C1. C1 is equal to 6 minus 3, which is just 3. So let's skip our C1. Let's put a sign here. Afterwards, we want to find for our C2, and how to do that, let's use our second initial condition, y derivative or y prime of 0 equals to 2. And so to find this, let's take the derivative of this general equation right here, our general solution. So the derivative of y is equals to c1 times cosine of 3x is just 3, negative 3, c1 sine of 3x plus c2 sine of 3x is just 3 c2 cosine of 3x, and the 3 just vanish because the derivative of a number or a constant is just 0. So after we get this, let's plug in our initial values. So y0 is equals to 2. Negative 3 c1 times sine of 0 is just 0. So 0 times negative 3 c1 is 0. 3 c2 times cosine of 0 is just 3 c2. So 3 c2 equals to 2, which make this c2 is equals to 2 over 3. So we've got our c1 and c2 right here, and let's plug our c1 and c2 into our general solution, and that will be our final solution for this superposition principle first example. So c1 is 3 cosine of 3x plus 2 over 3 sine of 3x. So this will be our final solution for this first example. Hey everyone, so this is our second example for today's superposition principle, as well as solving solutions for non-homogeneous linear ODEs. So to start off with this example, let's write down our superposition principle equation, which is just y equals to yc, the complementary solution, plus yp, the particular solution. And so let's start off by solving the yc first, or the complementary solution. So let's write this down as a homogeneous equation, which is 3 times the second derivative of y plus 3 times the first derivative minus 6y equals to 0. And we want this equation to be monic. And what do I mean by being monic is that in front here of the highest degree of the ODE, it must always be a constant multiplication of 1 for the equation to be monic. So let's divide the whole equation by 3. So we will get the second derivative of y plus the derivative of y minus 6 minus 2 actually, 2y equals to 0. And so we continue with our usual steps to solve for ODEs or ODE equations, which is turning this ODE into a characteristic polynomial and then take the roots of it, which is just r plus 2 times r minus 1, and everything here will be equals to 0. And so we know that our first root is negative 2, second root is positive 1. So we know our complementary solution, or YC, will just be C1 times E to the negative 2 times T, so plus C2 times E to the positive 1 times T is just T. So we get our complementary solution right here. Now, let's try and solve for our particular solution. However, notice that we've already been given our particular solution at the start of the problem, so we don't need to solve it. However, there are some cases that we need to solve it, but it will be discussed in the next lectures. So yp is just equals to negative 2t minus 3 over 2, as what the question states it is. So after we got yz and yp, remember everything is just y equals to, or let's just write down here, y equals to yc, which is c1 e to the negative 2t plus c2 e to the negative t minus 2t minus 3 over 2. And yes, we solved this in a superposition principle and we got the general solution of it, but we're not done here yet because we're given two initial value conditions or initial conditions that we need to use in order to solve for our unknowns, and which our unknowns are C1 and C2. So let's try and solve for our C1 and C2 and change this general solution into a particular solution by applying the initial conditions. So our first initial condition is y ln2 equals to 8. And so let's use our general solution right here by applying the values within it. C1 e to the C1 e to the negative 2 ln2 plus C2 e to the negative ln2, and then actually this is positive t, so this is going to be ln2 minus 2t, or 2 ln2 minus 3 over 2, and everything here equals to 8. And so we can simplify this, becomes 1 over 4, since negative 2 ln2 is just equals to ln2 to the power of negative 2, and then e to the power of ln 2 to the negative 2, we can just cross this out, so this just becomes 2 to the negative 2. So this 1 over 4 times c1 plus 2 c2 minus 2 ln2 minus 3 over 2 equals to 8. And to make our life easier, let's multiply the whole equation here by 4. So we don't need to deal with fractions. So this is c1 plus 8c2 minus 8 ln2 minus 6 equals to 32. And so moving all the constants to the right hand side, we will get C1 plus 8C2 equals to 8 ln2. 6 plus 32 is just 38. And we got here our first expression or linear equation. And we're going to use this expression later with the second expression. So let's put a mark down on this first expression. And so let's use our second initial condition to find the second expression, which is the derivative of y, same, ln2 for t, but this time is equal to 9. And so let's find the derivative of y first by taking the derivative of our general solution right here. The derivative of y is equals to c1 e to the negative 2t is negative 2t, c1 e to the negative 2t, and c2 e to the t is just c2 e to the t, minus 2t is negative minus 2, minus 0 over 2 is 0 because the derivative of a constant is just 0. And afterwards, let's plug in our values for the derivative equation. C1 e to the negative 2 times ln2 plus C2 e to the ln2 minus 2 equals to 9. And afterwards, we can simplify it further. Remember, e to the negative 2 ln2 is just 1 over 4. So negative 2 over 4 is negative 1 over 2 c1 plus 2c2 minus 2. And let's just move our, or actually let's keep it on the left hand side first, and we'll see why. And afterwards, let's multiply our whole equation here by negative 2, so we don't need to worry about fractions. So we get here c1 minus 4c2 plus 4 equals to negative 18. And let's move all the constants to the right hand side. Minus 18 minus 4 is negative 22. And so we got our second expression right here. And so we got two expressions, or a set or a system of linear equations which we can solve for the unknowns. And in here, let's use the elimination and substitution method because it's the fastest way for eliminating just two unknowns, or finding two unknowns actually. So let's write down our first expression right here and eliminate it. C1 plus 8 C2 equals to 8 ln 2 plus 38. And then the second expression is C1 minus 4 C2 equals to negative 22. And let's eliminate the C1 because it's the easiest right here. So 8 minus negative 4 is 12 C2 equals to 8L and 2. 38 minus negative 22 is positive 60. And dividing everything by 12, we will get 8 divided by 12 is just 8 divided by 4, 12 divided by 4, so 2 over 3. Plus 60 divided by 12 is 5. And so we got our C2 right here. Let's mark this down. And let's just plug in our C2 to our second linear equation right here because it's the easier one than the first one. We don't need to do much more arithmetic operations on it. C1 minus 4 times the C2 that we get, 2 over 3 times ln 2 plus 5 equals to negative 22. So distributing our negative 4 inside. So this is going to be negative 8 over 3 ln 2 minus 20 equals to negative 22, moving all the constants to the right hand side. So C1 is equals to 8 over 3 ln2. Negative 32 plus 20 is negative 2. So we got our second unknown here. And we solve all of our unknowns, which are C1 and C2. And let's go back to our general solution. Where is it? Our general solution is right here. So we're just going to use our C1 and C2 and plug both of them inside our general solution. So our general solution before is y equals to C1 times e to the negative 2. C1 we got 8 over 3 ln 2 minus 2. So let's put a bracket around here. Minus 2 times e to the negative 2t plus C2. C2 is 2 over 3 ln 2 plus 5 times e to the t. And then our particular solution at the start of the problem, which is just negative 2t minus 3 over 2. And so this is our final solution to the second example of solving solutions for non-homogeneous linear equation, non-linear homogeneous ODE equations, as well as superposition principle.